A farmer has a rectangular field sized 70 meters wide by 98 meters tall. They want to divide the field into the largest size square plots that use up all of the field with no wasted space. A square plot has equal sides that are a whole number, for example, 20 by 20 meters. The size could be any whole number, such as 40 meters or 70 meters. This plot tiles together, and any space not covered by the plot is wasted space. However, plots cannot go past the edge of the field. The goal is to find the largest plot size X that completely tiles a field size 70 by 98 meters with no wasted space. Then, could we generalize this for any sized field? Pause the video here if you'd like to try and solve this yourself. We could try every size square that fits in this field, and we'd eventually get the right one, but this becomes very inefficient as the size of the field gets bigger because it takes a linear number of steps equal to the size of the field. One thing we notice is if we want no wasted space horizontally, the plot size X must evenly divide the field's width. Similarly, to have no wasted space vertically, that same X must also divide evenly into the field's height. This means that the size of the plot X must be a divisor of both the width and the height. Putting this another way, X is a common divisor of both width and height, and we're trying to find the largest X, or the greatest common divisor of width and height. Around 300 BC, an ancient Greek mathematician named Euclid wrote a division algorithm in his treatise Elements. It is one of the oldest known algorithms that is still in common use, and is aptly named Euclid's algorithm, and it solves this exact problem in logarithmic time. The key insight that Euclid had was realizing that the greatest common divisor of two numbers does not change if we replace the largest number by its difference with the smallest number. For example, the greatest common divisor of 25 and 15 is 5. If we were to replace the bigger number 25 with the difference of 25 minus 15, that would be 10, and the greatest common divisor of 10 and 15 is still 5. If we did it again, the larger number is 15, subtract the smaller number 10, and we get 5. The greatest common divisor of 10 and 5 is still the same. And again, if we did 10 minus 5, and now that both numbers are 5, we directly know what the greatest common divisor is. This new set of numbers is always smaller than the last. And we can recursively apply this logic until both numbers are the same. And at that point, the number we're left with is the greatest common divisor. This might be a bit hard to understand just by looking at it, so let's see it in action. We start with our original field size 98 by 70 meters. The first square we can fit is 70 meters wide, and that leaves us with 98 minus 70, which is 28 meters in space above. So we're able to fit a 28 by 28 meter square into that, and then we're able to fit another 28 square next to it. At that point, we're left with a space that is 14 meters wide, so we can fit a 14 square into there, and we can fit another 14 square on top of that. And after that, we've used up all of the space perfectly. So that means 14 is the greatest common divisor between 98 and 70. This means 14 by 14 meters is the size of the largest size square plot that we can tile in our field perfectly. And with that, we have our answer. We can rewrite our pseudocode algorithm from earlier in Python like this. This concept of tiling multiple blocks is similar to subtracting the same number multiple times. Instead of doing that, we can use a modulo operator to do all of that in one go. This algorithm runs with logarithmic time complexity, related to O of h, where h is the number of digits of the smaller number. If we replace a recursive call with a while loop, we can make the Python code a bit cleaner also. And with that, we have Euclid's algorithm for finding the greatest common divisor for two numbers. I think it's so cool that an algorithm that was invented over 2300 years ago is still being used today. We still find it in places like solving equations or factoring polynomials, or even simplifying fractions. Good job, Euclid. Thanks again for watching, and see you all next time.